Hello everyone, welcome to my CCI Enterprise course. In this course, you will learn all the technology related to your CCI Enterprise journey. And in case if you are looking for the actual lab type of scenario and the solution, then you can reach out. You can send me email Ratnesh721 Kumar721, that is here, and then I will send you that detailed info that how my students they are preparing for their actual lab training. It will be almost similar that what you will expect in the exam. You can practice. I will help you. I will guide you for 1 month to clear this exam. I will help you step by step how to drill down um, the solution, drill down the technology into small pieces, and I will help you to pass your exam in first attempt. So go for this course. This will be a good place where you can learn the technology. But if you are serious about the CCI lab exam, then you can drop me an email and you can get the detailed info. All right, so let me stop this video, and if you watch this video, you can simply contact me and you can get the information related to the new update that we have in the CCI Enterprise Lab. In 1.1, we have to understand about troubleshooting the administrative distance related to routing protocols. First of all, we'll go and understand about the administrative distance, what's the use of administrative distance, how it is working. And then in the upcoming section, we'll go and understand the troubleshooting strategy related to AD values. Now, while we are talking about routing protocol, we know this term that first of all, these protocols, they will go and form the neighbor relationship. That means they will exchange their hello packets, find their neighbors, discover the neighbors, they will form the neighbor relationship. After that, they are building the topology table. They have to build the complete database, means complete roadmap, you can say, across the network or throughout the network. That is termed as a topology table. That means everything they have in the database. Now, on top of topology table, if they are running OSPF, they are running SPF algorithm. If you have EIGRP, it will use dual algorithm or dual algorithm to compute the best path out of this topology table. So out of everything, you are selecting the best path. That's the routing table. And then that routing table, the traffic is being used from source to destination. Okay. Now, what's the use of administrative distance? We know that all the protocols, they are associated with AD value. And this is one of the factor inside that how the devices, they are selecting the best path, correct? So the point being here is this, that administrative distance is nothing but it's termed as a trustworthiness or the believability of that particular route. So what does it mean? It's actually the comparative thing. So it means that if we have two different protocols and suppose I am a router, I am getting the same route from two different protocols. As per the lower AD value, I will trust the lower AD value route. So suppose if I am learning a route with respect to ISIS, whose AD value is 115, and with respect to RIP, whose AD value is 120. So I will prefer obviously ISIS because its trustworthiness is believability is high because its AD value is less. Suppose if I'm getting one route, the same route from ISIS, same route I'm getting via the static route. So obviously, I will go and trust the static route because its believability is more than ISIS. Its AD value is less. Okay. So now, do we have any mechanism that we can go and tune the AD value? Because the um, the AD distances, AD values, they have a local significance. So how I am learning, can I go and change it? Yes, we have the option that we can go and use the distance command to tune the AD value. But use it with caution, because if we are not using it with proper proper degree of administration, or if we're not using it in a proper manner, there are chance that it will create routing loops, black hole in a network. So if you are using the distance value, use it properly. You should know as a network engineer that where we are doing this path manipulation, how we are doing this path manipulation. Now, before showing this distance command, you can see one example here. So I am at router R1, I am getting one route. So you can see with the IGRP, whose AD value is 100. So two routes are coming. One is coming with IGRP, mark as a I, and one route is coming, same route is coming with a RIP as well. So 10,000 and 10,000 is coming via RIP, is coming via IGRP. Since IGRP having AD value 100 and RIP having AD value 120, so IGRP is winning. So that's why you can see here in the routing table, the IGRP routes getting installed either in R1 and R2. Both places you can see that IGRP routes, they're winning. Now, if I go to R1, so you can see I'm in R1. If I go inside the RIP and if I change the distance, so RIP distance, now I am doing the manipulation. I'm making it 90 instead of 120. So that means that R1, now when R1 will learn the route, you can see that AD value is 90. And now you can see that it is, this R1 is learning the same route via the RIP protocol. Although if you go and check the R2, still R2 is learning via IGRP. Correct. So it is using, if you go and change the trustworthiness, that means that you are manually changing how the routers, they are getting learning the routes. That's the one use case while we are doing some sort of traffic engineering, some sort of path manipulation or AD manipulation. The other important use case we have with AD value is the failover scenarios. Sometimes we are using it as a fallback link. So what does it mean? It means that we can go and utilize this with a static route. So in a static route, you can see that I have one primary path, but suppose if that primary path will go down, I have put one entry here in my routing table, the static route whose AD value is 250. So that means that my primary link or maybe Ethernet link, if it will go down, then it will go and use this dialer interface. It is not being used in first place because you can see it's a 250. It's way higher than whatever protocol we have. Now, if you go and use this, that means if my primary link will go down, this dialer interface will come into the picture, because now this dialer interface is being used as a fallback interface. All right, so let's stop here and we'll continue the troubleshooting section in the upcoming video. In this section, we are going to understand troubleshooting related to route redistribution, and I'm going to add administrative distance troubleshooting as well in that redistribution topic. So overall, we are going to cover 1.1 and 1.4 in this particular section. Now, before doing the troubleshooting, before checking that what actual troubleshooting we have, means I have prepared the lab here. So before going to the lab related to troubleshooting route redistribution, I just wanted to cover up first of all what is route redistribution and why we need it. Okay, we need route redistribution. Why? Because suppose if you are in multi-protocol environment, so there are chances that in the organization you may have different protocols running, OSPF, EIGRP, and some others as well. Now, if you want to learn or exchange the routes in between different routing protocols, then we have to go and enable or we have to do the route redistribution. So suppose EIGRP, if you want to send to OSPF, OSPF, you want to send to EIGRP. We need to do the redistribution. Now, there are some very important points that we should understand while doing the redistribution. So while you're doing the redistribution, the first thing is that one of your router that may work as a border router should have both the protocol running. So you can see router B has running EIGRP plus OSPF. That's the first thing. that one router understanding multiple protocol. Second important thing, we know that EIGRP metric value is different, OSPF metric value is different. Now, if you send EIGRP routes to OSPF, obviously EIGRP will lose its metric value, because once it is in OSPF domain, then that particular route will be known with their OSPF metric values, not the EIGRP metric values. Because here in this area, you have to do some sort of route manipulation, and that will be occur with respect to OSPF attribute. Um, Vice versa is also true if you are sending the OSPF within the EIGRP domain. So now the OSPF route, whatever metric it has, it will be known by the EIGRP metric. Correct. So these are two very important points. Apart from that, rest of the points we'll go and discuss. Now, so when we are doing the redistribution, the step for redistribution is easy. Suppose if you want to send IGRP to RIP, go to the RIP process and call IGRP. While you're calling the IGRP, give the route metric that will be RIP metric, correct? The RIP understand hop count or distance. Hop count basically number of routers in between. So you have to go and give the metric that RIP can understand. Vice versa, suppose if you want to send RIP inside IGRP, so go inside IGRP, and then, so you can see that we are inside IGRP, and then we are redistributing with IGRP metric like reliability, load, MTU, bandwidth delay, etc. Okay, so these are the basic three fundamentals that one router should have both the protocols running. They will lose their metrics. So while doing the redistribution, you have to take care about the metric value. Now, suppose if you want to make the metric constant throughout the protocols, throughout different routes that you have, then we have the option of manual metric as well. So we can go and use the default metric. So here you can see that you can go to the EIGRP call OSPF, and then you can put the default metric, bandwidth, delay, reliability, load, and MTU. Now, some of the protocols, if you're not putting the default metric, they will mark this as a zero metric and it will not advertise. Not the case in OSPF. OSPF having default metric as a 20. So that means still it will work. Okay, but some of the protocols, they have default metric 0, that we can go and list those protocols. Great. Finally, when we are doing the OSPF redistribution, you can see that by default they are type 2, and if you want to change it, you can go and use the OSPF type as a type 1. First thing. Second thing, the OSPF, they are taking EIGRP as a class full routing protocol unless classless or otherwise classless. So suppose if that is the case, that means you are redistributing EIGRP into OSPF, you are redistributing RIP inside OSPF. So you have to use one key called subnets. That means it is supporting a variable length mask or classless type of routing domains or the subnets. Great. So very good important points we have discussed, 4 5 very important point that we can list down all these very important points. Lastly, in this section, if you want to redistribute the static and connected routes, so that option is also there. Only one caution is there. If you go and use the keyword redistribute connected, that means whatever interfaces we have with the router, all these interfaces will get redistributed. So what we can do, we can go and create one route map. Route map I will cover later on. So we'll go and create one route map where we can match the interfaces, and then inside the protocol, we can call the route map with this. Obviously, when you call this route map, it will go and match only these interfaces. Right. So idea being here, select those interfaces, match inside the route map, and then redistribute this route map inside the protocol. Great. So now we have the lab section. I'm going to show you the lab scenario that we are going to discuss now. I have this lab topology here. What we'll do, that we have 6 router. You can see 1, 2, 3, 4, 5, and 6. And these two router number 3, or router C and router D, or 3 or 4. So router C and router D, they are working as a area router means they are running both the protocols OSPF and RIP. So what I will do, I will go and give the IP address. You can see the IP schema is very straightforward. To 192.168.1.x belonging to, or 0.0x belonging to OSPF, 10.1.0.0/24 or XX belongs to RIP. So anything belonging to 10 belongs to RIP, anything belonging to 192 in this lab belonging to OSPF. I have created certain loopbacks because when we manipulate routes, we need some extra network. So here you'll find the loopbacks. So this network, this network, this network, this network, they are the loopback. Rest of the connected interfaces are there. I'll do one thing. I'll go and log into the lab devices. I will show you the IP address and the OSPF configuration. Plus, once we will go and do the two-way redistribution, you'll find that there are issues related to routing loop. Okay, so first of all, what I will do, I will show you the configuration, and next section we'll go and discuss about the issue that we have. So here I am in the router number 1. You can see that IP address schema. It's easy and straightforward. And because this is router 1, so it is running only OSPF. So you can see that I'm advertising the OSPF. I just wanted to highlight. So here you can see that OSPF is running here. Okay. And let me quickly go and run the same command in all the routers. So I can go to router number 2. And here also, I just wanted to show you the IP first. So IP is over the interface and the loopback. Then you can see the router configuration means OSPF configuration. Although we have network only 3, 4, and 5 here. We don't have 1.0 and 2.0. So leave these two lines, first two lines. The rest is okay. Then I can go to router number 3. Oops, and show IP int brief. You can see here router number 3 is working bridge between OSPF and RIP, and you can see the protocols that are running here. So you can see that inside OSPF I am calling RIP with the metric with the subnets keyword, and inside OSPF I am calling, so inside RIP I am calling actually OSPF, and inside OSPF I am redistributing or calling RIP. So two-way redistribution is happening here, easy and straightforward. Finally, we can go to router number 4, the bottom router in the diagram, and you can always refer the diagram. So you can see we have checked router 1, router 2, router 3. We are checking that also running both the protocol, and here also you can see RIP and should see RIP and OSPF. So OSPF we are calling RIP, and RIP we are calling OSPF. I can see some distance command is there that I don't need. We need this distance command later on. So let me quickly go and remove this. I don't need this distance command. We will check later on the usability of this distance command. All right, and then let me quickly verify. Show run section router. Let's see, show run is a little bit slow here. All right, so RIP calling OSPF, OSPF calling RIP. That's okay. And then you have two other routers. They are purely inside the RIP domain. Correct? So here you can see show run section router. And likewise, the last device, router number 6. Here also you can check that the configuration, the interface configuration, and the router configuration. Okay, now since we have done two-way redistribution, so if you go and check the route over R3, so if I go here and check show IP route, you can see that router number 3, they are learning some network related to RIP via OSPF, and that is not good. Likewise, if you go and check show IP route for router number 4, we'll see that it is learning more routes via OSPF. That is not good. So in next section, we'll go and discuss about that, why this loop is happening. And next we'll go and remove certain problems from the network. We will see that what options we have to correct from such loops. In this section, I'm going to show you that what problem we have if we are doing the redistribution, and in the redistribution, if different protocols having different AD values, we know that lower will be selected. Now here you can see in the diagram that one side we have 192 network running OSPF, other side we have 10 network running RIP. Now when we'll do the two-way redistribution, a RIP network will come inside OSPF. Now since we have done the redistribution, obviously we want to send OSPF to RIP as well, but that's the thing. Now what will happen, and if you go and focus to this particular router, so what will happen that any of the routes, so for example 10.13.0, that is coming here 10.13.0. Now when OSPF will send this particular route to a RIP, first of all it will go to this particular router. Now this router, he is getting 10.13.0 with OSPF AD value 110, and he is getting the same route here, you can see, with 10.130 with the AD value of 120. So to whom he will learn? Obviously, he will go and install the OSPF route, and that's the loop. So same route that he should get from RIP, because maybe he is originator or near to originators. He's learning inside the RIP domain. The same route that he is advertising, he is getting. Okay, and that's a loop you will find here in this case, and that's the explanation we have. So this is termed as a routing loop. That means that we should go to router 1. So once there is loop, so once we'll go and detect the loop, there are methods that we can go and improve it. Correct. So I'm going to show you in the lab that once we will go and detect the loop, so I don't want to learn OSPF route in this interface. So I'll go inside router number 3, and I will use one distribute list applying in this direction, that in this direction I don't want to learn these routes. That is the RIP routes. That is one way. The second way that we can improve this, that we can go and lower the RIP AD. So lower the RIP AD means we'll go and make the RIP administrative distance as less than OSPF 70 or 50 or 40, etc. So that means that when this router have to learn the network, he will see OSPF coming with 110, RIP route that is coming with maybe AD 50. So that means it will go and install the RIP route, because we are changing the AD distance here, or maybe we can go and increase the OSPF external AD value to more than 120. Okay, so these are the methodologies we have. I'm going to show you this particular section, that how we can go and use the distribute list feature inside router number C, even router number D as well, or router number 2, router number 3, and router number 4. So R3 and R4, we are going to apply this particular rule. So let's go here. Let me quickly show you the problem first. If we are inside the router number 4 or 3, and if you go and check show IP route, you should learn 10 network. You can see 10 network is coming via the OSPF. That should not be the case. It should be a learning with the RIP process. So I'll do one thing. I'll go here, and first of all I'll go and create the access list. So access list 40, and then I want to deny certain routes. So I want to deny 10, 2, 3, 4, 0. So we can go and give this network 0000255. Let's create the ACL first, and then 3, and then 4 and 5, because these are the network belonging to RIP. Once we deny this, apart from these routes, what we want to allow everything. So I'll create one more statement that will permit everything except these routes, so permit any. Now, once we have the access list like this, then what we can do, we can go to the OSPF process, and inside OSPF process, we can go and use the distribute list. I want to apply in this particular interface. Oops. This particular interface, that is Gigi 0/1, because this interface we don't want to learn. Even here you can see that all the routes, all the RIP routes, my router is learning from this interface in terms of OSPF. So now we'll go and create the distribute list. Distribute list for 0. Let's see the options that we have in the inbound direction. And then the gig interface 0/1. Let's check the route. Do show IP route. And now you'll see that it is learning these routes via the RIP. Okay, so this is the routing loop you can see, and with the distribute list, what we have done, that we have corrected that particular loop. Now let's do this thing. Section access list. The same ACL call 40 that we have created, correct? Same ACL I will go and create inside router number 3 as well. And then we'll go to router OSPF1, distribute list for 0. And then we can go and apply this in the inbound direction to the gigabit Ethernet 0/1, correct? 0/1, and then we can go and check show IP route. Great. So you will see once the protocol will get converged, we are blocking OSPF on this interface. I should have a RIP route coming here. I should have RIP first of all forming. Show run section RIP. Do I have RIP which is getting learned here, or if some issue with any of the interface? But yeah, overall you can understood that the process that is working here. So if I go to router number 3, and let's see that what interfaces we have. So 0/2 part of this interface, 0/2 should have correct routing and all those configure. It should be pairing with router number 5, 0/1. So let's see. So if I ping here 10.1.1.5 should be the IP. Let's see here. Router number 5. So 10 dot, that's correct. 0/1 and show run section rep. Okay, and in router number 3, RIP version 2, network show IP route. So you can see that it took some time to converge because RIP hello packets, they have some delay in that. But you can see that 23-second back, we have this routing update. Great. So this way we can go and troubleshoot our network. We can go and correct the loop, means we can prevent from the loop. All right, so we are good here. We can now go and stop this particular section. In this section, I'm going to cover 1.2, that is troubleshooting route map for any routing protocol. First of all, we'll go and discuss the theory related to route map. And then in the next section, we'll go and perform the lab related to troubleshooting. So that's about 1.2. About 1.3, in the specific protocol, suppose if you go and study EIGRP, and after this section, we have EIGRP after a few videos. So in that EIGRP video, I will go and cover different type of mechanism related to loop prevention. So when I go and give you detail about specific protocol like EIGRP, OSP, or BGP as per our syllabus, then I will go and cover section 1.3 because it seems like only one bullet point, but we should understand the routing protocol, the mechanism, and then we can go and apply different type of rules to protect from the routing loops. For example, in the previous section, you have seen that with help of filtering, so we have used something called distribute list, and then we have protected from the loop. And in upcoming section, in upcoming lab section, I'm going to tag a route map with the tagging. So route map we'll understand in this recording, and we are going to use some sort of tag. Tag is nice way to protect from the loop, and we'll perform the lab task. So slowly we'll build the concept and we'll perform the troubleshooting lab as well. All right, so let's understand route map. Before understanding route map, I have few small concepts such as prefix list and distribute list to discuss. And then I will go and check that route map and how it is building, how we can go and apply the route map, etc. Prefix list. We know at this point of time that how access list, ACLs, they are working. Likewise, we have prefix list as well. Either you can use ACL, access control list, or you can go and use prefix list. There is no much difference. Um, Although the use of ACL, so ACL is working as a placeholder, and ACL, once you create access control list, you can use inside route map policy, distribute list, NAT policy. There are so many places that we can go and use ACLs. But prefix list use, you'll find mostly we are using inside the route map, and we are playing around with BGP attributes. Mostly we are using there, although we can use with distribute list as well. So what's the use? When we are talking about prefix list, so it is adding the network. So two parts are there. So it will go and add the network, and plus it will go match. So match the network first and then match the subnet mask. So two matching criterias actually are there for prefix list, and it's a nicer way to match the IP and the subnet, network and the subnet, correct? So here you can see the example, two examples are there. Suppose if you are matching, let's just start with a smaller one. So suppose if I have to go and match 10.1.0/24 exact match, so I can go and use this. Although if you want to match the variable length, suppose if you want to match 24 till 30, you can go and use /24 less than equal to 30. And suppose if you want to match 24 greater than 26 and less than 30, so you can go and use this statement. So it depends that what type of matching criteria we have. According to that, we can go and match. Some explanations are here. You can have a look. Great. Now, if you want to match everything, then you can start with 0 up to 32. That means you are matching everything. Match all prefixes. All right, so this is about the prefix list. Then what about distribute list? we have performed the lab task in previous section related to distribute list. So either I have access list or prefix list. I can go and match that entry inside my distribute list. So distribute list, uh, I want to match this access list or prefix list, and then we can go and apply this over the routing process in and out, or in or out. So either inbound or outbound we can use. Now different protocol behave differently, at least OSPF and ISIS, because they have their own LSA type of databases. So when you are applying the distribute list to OSPF and ISIS, you have to be cautious because they have to. So whenever we are applying their distribute list, they have to go and match that distribute list with their link state database. Okay. Great. So let's talk about route map, our main area in this particular section, that we have to understood the route map, how it is used, and then how we can do the troubleshooting related to route map. Route map, clearly you can see here in the slide that they are going to control the redistribution between routing protocol, one big use of route map. Other big use, playing around the attribute with respect to BGP, and it's a huge, because BGP itself is a big protocol. It is something we are telling that BGP is a protocol for internet. It's a huge, it's too many attributes BGP having. Now we can go and match and set the attributes related to BGP with respect to route map. So if you want to tune the BGP attributes, route map is the best tool. And then finally we can go and use the policy based routing as well. We have separate section for policy based routing, PBR. So we'll go and discuss more in that particular section. Okay, great. So how the route map is working now, it's actually easy. It's like programming type of a structure. So you can go and create, say, a route map and then a statement, say permit or deny 10. Now inside 10 you can go and match. So you have condition match, you have condition set. Okay. So likewise, you can go to line number 20, line number 30, line number 40, etc. By end of all the lines, what you have implicit deny. So that means if you are not matching by the end of the line, it will go and drop everything. Like that, we can think about the logic. Okay, so let me quickly highlight that line here. So here you can see, however, ACLs can merely permit or deny, while route map can additionally modify perform. It's telling that, okay, I'm matching one condition related to ACL. Now, if you are doing some permit deny inside the ACL, again, you can go and modify that thing inside the route map. So the statement that we have inside the ACLs, that also we can go and change here. Okay. So route map is actually easy. Let me show you with respect to the examples. So how you can go and create, first of all, you can go and create either ACL or prefix list. Then you can go and create the route map, match the address, and then set the next hop. This is actually policy based routing example, PBR. So you're matching certain IPs, and then you're setting those IP next hop somewhere. So these IPs, they will think that their next hop. So suppose if you have multiple next hop, you can go and apply this policy on this interface. So for some subnets, the next hop will be this, some subnet next hop will be this. So next line, again, you can go and create the access list too with IP addresses like 2111, etc. and next hop 2.1. Okay. So you can go and change the next hop attribute as well with related to route map. That's one example. Apart from that, I'm going to show you all three examples I have in this video. Now before reaching there, let's discuss a little bit more about route map. So route map, we can write our points. So first of all, we are creating the policies with respect to sequence. So sequence 10, 20, 30, etc. We are matching. You can go and use the match and the set commands, correct? Now, if you go and match the ACLs like 1, 2, 3, suppose you have ACL1, ACL2, ACL3, or ACL, ABC, whatever name of ACL, if you go and give like this, that means it will go and match the OR condition. This means it is matching the OR condition. Now, if you go and give that match statement line by line, so line 1, line 2, line 3, like that. So this will go and match the AND condition. We know that what is the use of OR and AND. OR means either this or this or this. AND means everything has to match. That's the AND condition. Okay. So how we are writing the policy, it is also very important. Then what we can do, we can go and set. So you can see that we can go and match the address. We can set the weight. We can set the preference. This is related to BGP configuration. So let me show you one by one all these examples. So here you can see that one of the example related to route map, we are creating the route map called my map, matching the address, match the interface, then we are matching the prefix list, then for that prefix list to next hop, match the metric, match the route type, match the tag, match the community. See how deep we can go inside the policy, inside the route map policy, correct? Likewise, we can go and build the BGP related policy as well. So here you can see BGP related policy, create the route map. If you have any interface, set it, then go and match the metric, tag, community, local preference, weight, IP preference. Each and everything inside the BGP attribute, the route maps they are supporting. Okay, here you can see that once we have the policy, so here you can see that we can go and set the metric, and then over the BGP process, so router BGP, we are applying this route map to the neighbor, okay, in the outward direction. So you can create the policy like this. So route map policy you have created, and then with respect to neighbor, you can go BGP neighbor, you can go and apply it. Okay, redistribution, how we are applying route map with respect to redistribution, you can go and create the ACL or prefix list, create the route map policy. So route map policy, my map, match the address 1, set the tag 150, and then you can go to the routing process, router EIGRP. So see, in OSPF, we are redistributing EIGRP. Correct. So go to OSPF, redistribute EIGRP10, metric subnets, these things we have discussed earlier, that if you are redistributing RIP or IGRP or EIGRP, you have to go and use subnets and then route map my map. That means this program will call this program, and this program will call these ACLs. Like it's like different objects you are creating in terms of programming. So this is one of your object which is called here. So it will go and check his own name, and then it will go and call this ACL. Great. One last example I have related to PVR, policy based routing. Again, it's easy. Now you can create the route map policy. First of all, create the ACL, create the route map policy, permit 10, match the address, set the next hop, and then this policy you have to apply over the interface. So here you can see, build the policy and then apply the policy. In case of PBR, policy-based routing, we are applying the policy to the interface. In case of route redistribution, we are applying with the redistribute keyword over the routing process. And with respect to BGP, we are applying to the neighbor, either inbound or outbound. Okay, great. So this is the usability use case with the route map. We can stop here, and in the next section we have to work on one troubleshooting ticket. In this section we have to work related to route map troubleshooting. So I'm going to show you how we can go and check the steps when we have issue in a network with respect to route map. Maybe redistribution is not working with respect to route map properly. How we can go and tag, how we can go and check different type of attributes related to route map, and even if we want, we can go and do the filtering as well. So all these steps related to troubleshooting, I'm going to show you in the lab. Now, before starting that lab, I just wanted to give you the hint here that what we are going to do perform in the lab. So you can see that we have the lab set up, and previously we have done a few of the lab tasks here. Now, in this particular lab, you can see that we have two different routing domain, OSPF and RIP. And in previous section, we have done some sort of redistribution in between them. But while doing the redistribution, we found that a routing loop start occurring, or maybe chances that for router number 2 to reach router number 1 loop back, he may go via RIP and then he will reach to router number 2 loop back. This is termed as a suboptimal routing or suboptimal path, because he is not believing or trusting to its direct peer, although he is finding better way, is less metric or some loop or some suboptimal path to reach to that particular destination. So how we can go and remove the loop with respect to tagging? Tagging is one nice feature we have inside route map. We can tag the routes, and while sending or receiving, we can use that tag. So what I can do here, I can go in this lab setup. I will tag OSPF domain as a 44. So OSPF route, whenever they will go to other domain, those routes they will get tagged with tag 44. And RIP protocol, we are going to tag a RIP with tag 33. That means when RIP route will go to other domain, they will come with tag 33. Now, what will happen with this, and what good thing will happen with this particular feature? So once we have tagging, so we have tagged the route. Now, what will happen? Suppose if we do redistribution and RIP will go and get the routes with tag 33, he will drop it. Correct. Likewise, if we do the redistribution and suppose if OSPF will go and get the route with tag 44, he will drop it. Why? Because this is my route. I have the trust within my network. I don't want to get the same route from others. And that's the whole concept that we can use to break this suboptimal routing. Now, when we have the loop or suboptimal routing, sometimes it is termed as a route feedback as well. You are getting same route from other domain. That is not good. So we are going to use this technique of tagging, not only tagging, but we can go and set certain attributes as well. Not only the tag attribute, but we can go and set the metric values as well. We can go and put some sort of ACL, access control list as well. And that's the whole idea behind this particular section 1.2. So what I will do here, let's go and log in to the lab where we have the break scenario. Means I'm going to show you one lab where we have some issues. We have to dig deeper inside the lab. We have to correct each and everything and make it proper and working. So while doing that, obviously we will learn that how we can correct the route map. At this point of time, we are well aware about our lab setup. So if you go to R1, let's go to R1 where we have OSPF routing domain, or OSPF is configured in between R1, R2, R3, R4, first portion of R3 and R4. So if we go here and if you go and verify the OSPF configuration, you can see flat OSPF configuration, no distribution. Means obviously here we don't have distribution. We have distribution on the border routers like R3 and R4, but in R1 and R2 you do not have redistribution. But if you go and check show IP route, do I am getting routes from a RIP domain? Let's see. So it seems that a redistribution is working and we are getting the route, and you can see the AD values 20 is type E2. That's good. And if we go and check R6, let's see in R6, do R6 getting the routes from OSPF? And let's see. So here you can see that R6, it is not getting the routes from OSPF. And now if I go here and check any of the routes, show IP route 10.1.1.0, let's see if we have any tagging. So tag is not there in this route. Okay, that means we have to go and check our R3 where we have done the redistribution. So over R3, if we go and check the configuration, although I can see some route map configure, OSPF to RIP, OSPF to RIP, the RIP to OSPF, but it is somewhere it is configured, somewhere it is not configured. So what I'll do here, let's do the troubleshooting. Let's first of all check the route map. And to make this little bit easier, what I will do that we will go and do the one-way redistribution. So we'll correct the routes in this direction first. RIP to OSPF. Okay, that means we have to go inside OSPF and call the RIP. And then we will go and correct in this direction. So first in this direction, second in this direction. So let's check router 3 and router 4 and this direction that is coming from RIP to OSPF. Great. Let's go back to the lab. So here we are in R3. Let's check show run section route map. Just wanted to correct the route map that is coming RIP to OSPF. So I'm focused on RIP to OSPF. Do we have RIP to OSPF? Yeah, here you have. So I can see here clearly that we have the route map called RIP to OSPF, how it is configured. You can see that some deny statement is there, some IP match statements are there. Okay, so what is the idea? Idea here is this, that it is going from RIP to OSPF. That means, let me write here. So route map, and this route map that is RIP to OSPF, oops, route map, RIP to OSPF, it should deny, and what it should deny? It should deny tag 44. See, OSPF don't want tag 44 route. So that means that this statement is correct. OSPF do not want, because OSPF having tag 44. You don't need this. So first statement is 100% correct inside the route map. What about second statement? So I will go and second statement, I'll start with permit 10. Now second statement, you can see here that we are not setting any tag. So see, this route is coming from where? OSPF. Sorry, this route is coming from where? RIP to OSPF, RIP. So RIP should having tag 33. Correct. And then you have match IP address permit any. Now we have to go and check what is this ACL. Is it permit everything, or is it permit only RIP domain like 10.1.10, 10.1.20, etc., etc. But permit any will also work. But if you want tight filtering, you can go and check the specific routing, specific ACL. Correct. So let's see here, do show, and then let me show you the route map, and the route map related to RIP coming to OSPF. So let's focus on RIP coming to OSPF. Deny 44, that is 100% correct. Then permit 20, the match address, I will show you this as well. Show run section permit any, what is that? And let me use 2. So you can see that permit any is permitting everything. So this is also correct. If you have any misinformation in ACL, that will also not work perfectly. So this is also okay. And setting the tag with 33, that is also okay. So that means if you go here to R1, and now if you go and check the show IP route 10.1.10, this 10.1.10, since we have set the tag as 33, it should have that. So we'll wait. Now I can see here that metric is 20. That means that we have to go and check the redistribute statement as well. So we'll go and check the redistribute statement as well here. So we'll see here, so run section router. And here redistribute. So we are going inside router OSPF 1, and then we need to redistribute. See, we have two options here. Either we can redistribute RIP and set the metric value here, correct? So I can go here, redistribute to RIP metric, and because RIP is coming to OSPF, so I have to give OSPF type of metric value here. I can go and give, correct? And you can see here the statement to redistribute RIP subnets. Remember, in the theoretical section, I told you that OSPF by default, if you do not use any metric, it will give a metric as 20. And that's the reason here you can see that this metric value is 20. Okay. So the metric value is 20 by default because we are not giving any specific thing. Either I can go and change this statement here, OSPF. Even I can see that when we are going to OSPF, we are not giving our route map as well. So everything is redistributing here default, correct? So first of all, I should go here to OSPF and I should remove this statement. First remove this. Once it get removed, let's go here. No redistribution, that means it should not get any route, and it may get because there is other peer also, router number D, who can send. So I think there also it is not coming. So you can see we have removed the redistribution, things blocked. Now redistribute RIP, the route map, what's the name? The name is RIP is going inside OSPF, correct? So RIP to OSPF, enter. Now again, I'm not giving the metric value here. Metric value, if we do not give, it will take default as a 20. Enter. Now we'll go back here. You can verify. And let's see, the route should come. See, you can see the routes are coming here. And now if you go and check this specific route, so you should have the tag. See, tag is also coming. So these checks are correct, but the metric is 20. And if you want to check the metric, again, you can go and change the attribute. So I can go inside the route map. The name is RIP to OSPF. The statement is permit 20. And here I can set the metric. And metric, I can say I'll give 11. And then I can set the other attribute as well. Suppose if you want type 1, oops, type 1, because by default here you can see it was taking type 2, OSPF OE2. And if you do here, oops, if you go and check the IP route, you will see that OE1, and you can see this 11 plus some 1 for gig interface. The cost value for gig interface is 1. So 11 plus 112. So now it is working perfectly in this direction. From where to where? It is working perfectly from RIP to OSPF, correct? Now, if you go and check the OSPF to RIP redistribution, so let's see that. So now we have to go inside RIP. We can go and use the OSPF to RIP. So route map configuration application to interface is correct. Now we can go and check the OSPF to RIP route map, and here you'll see. So now what we are doing, RIP should not match the tag 33 is 100% correct as per the logic. In permit 20 statement, you can see that match the tag. This is not correct. And set the metric is correct. So only one correction I need to do, that we can go here. Oops. We can go here to a statement number 20. And once we are inside a statement number 20, then I should remove the match statement because, oops, because we want to set this. OSPF is going to set this. So I should go and do no match tag 44 because we want to set the tag 44, and done. Now if you go to R4, and you can go and check this, show IP route. Now, same configuration as mirror configuration you have to do for router number 3 or router number D as well. Now here you can see that when we are getting this 192, you can see it's getting metric as a 3. That means 2. We have set here 2. Okay, if you go and check, set the metric as say 13. And now if you go to here, if you check, so you should see change because RIP updates, they are taking some time. See, it's become 14 now. So now our two-way redistribution, troubleshooting, route map, their filters, their tag attributes, I have covered each and everything in this particular section. Let us see that what we have covered so far and what are the topics I'm going to cover in this section. So we have covered 1.1 troubleshooting AD value. Then in the previous section, we have done the troubleshooting related to a route map, and even we have done troubleshooting related to loop prevention as well. Now, loop prevention with respect to route map tagging, with respect to distribute list, and with respect to if you want to change the AD distance values. Okay, so all these things we have covered earlier. Then in 1.4, we have redistribution, troubleshoot redistribution between routing protocol. And this also very much covered in the previous section, because in previous sections, we have done the troubleshooting with respect to RIP and OSPF and RIP. And then we have checked the attributes related to route map. We have done the troubleshooting as well. Then we have 1.5. 1.5, I'm going to put a small lab related to 1.5 inside EIGRP section. And in the EIGRP troubleshooting section, again, we will go and we will check more on the troubleshooting related to manual auto summarization. So 1.5 you will get later on in the specific protocol section. Now, once we complete up to section number 1.1 up to 1.5, then we have section 1.6 where we have to configure and verify the policy-based routing, PBR, correct? Now, we have learned this thing in route map, that in route map, we have one specific use case that with respect to route map policy, we can go and create PBR policies as well. That I'm going to show you here in this particular section. So this thing we have discussed earlier in the in the route map theory, that you can go and create the ACL. So you have the ACL, then you can go and create the route map, and inside route map, you can go and match and set the attribute. Correct. So match the ACL and set the next hop, whatever gateway you have, and then you can go and apply this policy over the interface. This is one of the simplest form of PBR. We are going to use this logic here in our lab. So what we are going to do in our lab, you can see the topology. I have one router where one portion is belonging to LAN, local area network, and other portion it has ISP1, and other portion it has ISP2. In ISP also, while going via the ISP, I have given one destination 10.1.1.3. That's the router number 6 in the lab topology. So that means when you have host 1, so these routers you can assume as a host 1 and host 2. So host 1 and host 2, then when they will go and reach to their destination, so host 1 can go like this. So before applying the PBR, I'm going to apply policy based routing in this particular router. And if you do not apply the PBR, that means host to reach this particular destination, host 1 can go via this path or can go via this path as well. But if we go and apply the specific route PBR, policy-based routing or routing-based policy, whatever we can tell it. So PBR, policy-based routing. So what will happen that few of the subnets, so for example, host 1 and other subnets, we can prefer in one direction, correct? So what will happen that few of the destination will go in this direction via this gateway, via this ISP gateway, and few of the destinations can be reachable via this path along with this gateway. And that's the whole idea. So you can segregate the traffic over one path versus two paths. So if we have two exit gateways, some of the traffic you can force as a next hop. So what I can do, I can go and hard code that next hop for certain IPs will be this. And for certain IPs, they host two related IPs, the next hop will be this router. So the destination will be reachable in this direction. Okay, so I'm going to show you the lab. Here you can see in the lab IP schema, you can see it's straightforward. I will do and do basic static routing configurations here. Important configuration I will do like policy based routing configuration I will do, and host 1 and host 2, these IP addresses are 192.168.1.10 and he has 1.20. I'm going to create the ACL related to host 1 and host 2 as well. So let me quickly go and show you this. So here, if I go to router 1, the which is working as a host 1, and let me show you the destination IP as well. So destination IP is, let's see, it is 10.113, and if I go to the host 1, if I ping to this IP, you can see it is pingable, and if I go and do the trace route to this particular IP, so trace route is in progress. Likewise, I can go to host number 2, and let's ping first. So pingable, and if I go and do the trace route, let's see, before applying any policy, how these hosts, they are reaching to their destination. So it is going to first gateway, and once it is there in the first gateway, then let's see that which path. So it is going via ISP1. Remember 200 is for ISP1, and let's see that how he is going. So let's see, it is also, so both the host, they are going via 200, correct? Now what I will do, I'll make the change that host 1 should go via 200, or maybe I can make this as a 201. So let's do crisscross. Host 1 will go via 202. Actually 202 is the IP. Let me quickly show the IP as well. So the ISP IPs, if I go and enable show IP int brief, you can see that you have two IP, 200.111 and 200, 200.2.111. So one ISP versus other ISP, the top ISP versus the bottom ISP. Okay, and now crisscross means that host 1 should go via 202, correct? So let me show you how we can go and create. I can go here and first of all I can create the IP access list, host 1 via ISP2, or make it simple, host 1 ISP2, that's the name. Then I should go and give a standard here. You can go and give the keyword called a standard, and then you can go and you can do permit host 192.168.1.10, correct? Likewise, I'll create one more. So this time I'll create host 2 via ISP1. This is just the name, and this time I will give the IP, host 2 IP is 20. Okay, so now I have the ACL that will be consumed inside the route map. So we'll go and create one route map policy, name ISP prefer, okay, and then permit 10, match the IP address. What IP address? So host 1 via ISP2, correct? And then set the next hop, set the IP next hop will be, we know that host 1 ISP2 means 202.1.1.2. So host 1 IP, that is nothing but 192.168.1.1 is preferred by ISP2. Then I'll go and create the other statement, that is statement number 20. And this time what we'll do, we'll match the IP address that will be host 2 via ISP1 and IP next hop, and set the IP next hop will be 200.1.1.2. Okay, now once we create this policy, we have to go and apply this policy to the interface, to the LAN interface. But before applying that interface, let's run this just one more time, because we should be clear that how the path is before the policy and after the policy. So meanwhile this trace is going on, I will go quickly. I will show you that where you can go and apply this. You should go to the LAN interface, that is gigi 0/1. And here you can go and apply the IP, let's see, policy, route map, and the policy is ISP prefer. I will not press enter here. I'll come back and press enter later on. Let's see the path. So here you can see that host 1 is going via ISP 1 as per this trace before applying the policy. Both they are going via the ISP 1. I'll go here and press enter. So policy is applicable now. I will restart this trace route from R1 and from R2. And meanwhile the trace is going on, I can show you the hit count. So now if you want to see the hit count, show route map and your ISP, your route map name, and press enter. So here you can see that you have packets. So for host 1 ISP 2 packets, for host 2 ISP 1 you have the packets, and you can see the packet 11.7. Now if I go press enter, it should increase. So this time 18 packet, 17 packet. That means that traffic is going, hitting these rules at least. And clearly you can see that now host 2 is going via the next set hop, that is 202 as ISP2. And here you can see that it is going via the ISP1. So see that with respect to policy map, how we can play around with the next hop and we can load balance the traffic. So not only that we are changing the next hop, but we are playing around with the traffic as well to load balance the traffic as well. All right, let's just stop here. Virtual routing and forwarding. What is the use of VRF? When you are creating virtual routing and forwarding instance, so at that time you can segregate or segment the routing table. So for example, you have one global routing table, and then you may have a routing table for segmented, or for example, you can think like for customer A, you have one, customer B, you have one, customer C, you have one, like that. So it's like segmentation in routing. And what's the use case for that? So you may have business VPN services, network segmentation, data center access, etc. Now, this term that VRF that we are seeing here is actually layer 3 virtualization in terms of routing. But if you see and verify that, do you have any layer 2 virtualization technique? Yes, we have VLAN, virtual LAN, as a layer 2 virtualization technique, where you have, say for example, every VLAN having their own spanning tree instance. Every VLAN has its own MAC forwarding table. Likewise, if you go and check VRF, you'll find that all the VRFs, they have their own CIF, they have their own routing processes. Means most of the routing protocols, they are supporting VRF. And in the diagram, you can see that you have one global table, and then you can have VRF. So what we are doing that we are creating a VRF, and then we are associating that VRF to one of the L3 interface. So that means that one L3 interface, or one interface specifically, can have only one VRF. And later in the lab section, you'll come to know about this. Now we have various techniques related to VRF to provide fast switching or fast pathing. VRF Lite and then MPLS. MPLS is quite a bit popular. So what's the idea behind this is that you may have end-to-end segmentation. So suppose if I have diagram, so here you can see that maybe you have one end where you have VRF A and VRF B, and then you want this segregation, or you want this virtual routing forwarding instance to propagate throughout the network, means end-to-end uh, routing instance or end-to-end segmentation. Now, if you go and use VRF Lite, so in that case, whatever devices you have in between, here you can see, although you have only one switch in between, but it is showing green and red, means you have two VRF, two routing forwarding instance, two inside process or two virtualization inside one box. We can think like that. So the idea here is that if you are using VRF Lite, then you have to go and enable VRF Lite to all the devices. And that's the problem, that VRF Lite, although they are very easy to use, but they are not scalable. So that's the reason we are using MPLS, multi-protocol label switching, where again you are using LDP as a protocol to create the labels and then to exchange the label. Okay, so this is one of the use of the VRF. Although we are going to have, so we are going to perform one lab, and in that lab you will see use. Let us perform the lab task related to VRF Lite. Now in the diagram you can see that we have two sides. One side where we are going to configure the VRF. Other side we have the global routing table. One side I'm going to put the address space, so you can see the same address spaces that we are going to use in router 1 and router 2. You can see loopback 1 having IP 1111, but loopback 2 having IP 1111. One is inside VRF, but other one is inside the global routing, and you will see the configuration. I'm going to show you the configuration snippet, and I'm going to share all this configuration as well. Although we are going to run EIGRP, either it's a global routing table or it's an instance inside VRF, everywhere we are going to use the EIGRP as a routing. All right, so let me go and log into all the devices, and I will show you the configuration for all these devices, what configurations we have related to these devices. You can refer the topology. Topology is straightforward, that router 1 is connected with router 2 again is connected with router 3 and router 4. Now one side of the topology you can see, so let me quickly show you that topology one more time. One side of the topology you can see that we have VRF Lite configuration, that is from R1, R2, R4, correct? So here we have the VRF Lite. So here we are going to do the testing, ping testing with respect to VRF. And one side R1, R2, R3, it is configured as a normal global routing table. Okay, great. So let's go and let me show you first of all the IP addresses, and then I will show you all the rest of the configuration. You can see here that we have loopback 1, loopback 2, and if you go and check show and int loopback 1, loopback 1 we have created put inside the VRF. That means that it is going to connect from R1, R2 to R4. And if you go and check show VRF, let me show you the VRF. So we have VRF, and see this inside this VRF, we have interface loopback 1, and we have interface gig 0/1. Same address space, see 10.1 and 10.1 for both the interfaces. One interface, so CDP neighbor, one interface that is going actually 01 and 02, both are going from R1 to R2. We have two link going from R1 to R2. And if I go inside R2, let me show you the IP schema. So R2 is a bridge between R1, R3, and R4. And here you can see the connection with R1 and then connection with R3 and R4. 03 connected with R3 and 04 connected with R4. Let me show you the show CDP neighbor. So you can see here R3 is connected with 03, R1 connected with 01 and 02 interfaces. R4 is connected with 0/4. Okay, so straightforward. And again, here also you can go and check the VRF, show VRF. You can see the interface is loopback 0, gig 01, that's going towards router number 1, and gig 04, that is going towards router number 4. Rest, these devices, they don't need VRF light configuration. And here you have very easy, straightforward configuration. So here you can see that you have two interfaces. One is loopback, just to add one extra interface for testing purpose. And even in R4 as well, if you go and see, the configuration is very simple and straightforward. Now here, if you go and check the EIGRP, you'll find that EIGRP configuration is also very straightforward. We are starting the EIGRP process and advertising the network. Likewise, inside R3 also, you'll find the EIGRP configuration is easy and straightforward. But we have interesting configuration related to EIGRP here in R1. So let me show you here. We are using EIGRP, name is VRF underscore light, and then we are using the address family. First of all, you can see that we have the global type of address family. That's the unicast, this address family. Autonomous system, we are using one. And inside the topology base, you can see I'm advertising loopback one, whose IP is 11111. And then we have the other interface that is going from R1 to R2, correct? That is inside the global routing table. So let me quickly confirm here that which interface is there inside the VRF. So if you go and check show VRF, actually loopback one inside VRF. So this IP is actually the first IP that you are seeing here inside loopback. This is loopback 2 address. So inside global routing table, I have loopback 2 and this IP because they are going towards R3. So R1 to R2 to R3 where we have global routing table, correct? And then this portion of configuration is belonging to actually loopback 1, and then this is belonging to R1 to R2, that is that we want to send towards R4. So gig 0/1. Okay, this particular IP. So one IP we are advertising inside where we are advertising inside the address family unicast, but it is VRF instance, correct? And one IP is global. Likewise, we can go and check the R2 EIGRP configuration. So if you go and check R2 EIGRP configuration, you'll see that one IP should be as a global and one IP should be as a part of a VRF. So very much similar configuration. Now the partition. So from R1, if you go and check show IP EIGRP neighbor, which neighbors are part of VRF here, you can see it is telling that is a part EIGRP IPv4 VRF. The name is VRF Lite. And if I can do detail, so I can show you the detail about that. So I can see that neighbor is up. Let me show you show IP EIGRP neighbors, and then detail. If I can show you some more information about any of the interfaces that we have. Yep. So EIGRP is not in a requested interface because we are actually running network based configuration. So I can see here that one interface, that's gig 0/2, we have EIGRP enable on that, and show run section EIGRP. Let's see the configuration. All right, so 0/2, we can see that EIGRP is there. Now what I want to show you here, it's very important. So if you go and check show IP route and VRF VPN underscore A, you should learn the EIGRP specific route. See, router number 4. I'm learning. Even I'm learning on loopback, that is belonging to which interface. You can see it's coming via 0/1. So one is specific uh, subnet that is belonging to router number 2, that is part of VPN A or VRF. So here you can see that we are learning correct routes 22224444. Now if I go here and if I do show IP route EIGRP with respect to global routing table, so you should see 3 here. You can see 3. You are seeing 222 as well because we have 2 IP addresses. Remember, one is loopback 1, one is loopback 2. One is part of VRF, one is under global routing table. Not only that we are seeing the VRF light, but we are seeing that the usability of IP addresses as well. So let's do the testing. Now, if I want to do the testing with related to my VRF VPN A and the destination we know towards router number 4, we are going via the VRF, correct? And source is, we know that our loopback 1 having IP address 111, and you can see here sure and interface loopback 1 is a part of VRF. Correct, so it's going properly, there is no problem. And if you do the trace route, you will find that yes, it should go from R1 to R2 to R4. So VPN A and the destination is 4444 and the source is loopback 1. Okay, so first hop should be router number 2 and then the second hop should be router number 4. So it should follow that particular path. Okay, so now at this point of time, we are testing the path from R1 to R2 to R4. Now next we'll go and test the path from R1 to R2 to R3. Okay, so same type of test, ping test and trace route I'm going to do. Ping because this time we are inside the global routing table and I can give the source as a loopback 2, correct? Because this is under the global routing table. Likewise, we can go and do the trace route with the source of loopback 2. All right, so this is the lab related to VRF Lite. What I will do that I will put the configuration file. So you can also go and check the router 1, 2, 3, and 4 configuration. Although router number 3 and router number 4 configuration is easier, straightforward. Router number 1 and 2, what we are doing, we're going inside the EIGRP address family and then we are configuring the global routing table and we are configuring the routing under the VRF. So here also you can see that all the test pass. That means we are good to stop this particular lab. Next important topic, we have BFD. BFD, that's bidirectional forward detection, providing fast failure detection with respect to different type of media types, encapsulation, topologies, and routing protocols. Now, how BFD is doing that, they are working in sub-seconds. So that means that if other protocol, they are using 10 seconds to send the hello packets and then they get timers of, for example, 40 seconds to detect that the peer is not responding. With respect to that, BFD is using milliseconds to detect that. And BFD, so not only that, they detecting the failure or detecting the neighbor unreachability, etc. BFD is less CPU intensive, and that's the one very important thing. And second thing is that BFD makes network profiling and planning easier. Okay, so what are the things that BFD is providing us? BFD is providing the fast failure detection. It is less intensive to CPU. It is easier to do profiling and planning, etc. Okay, and that's why BFD is quite popular and used almost everywhere. Some of the protocol internally they are using BFD. For example, Cisco SD-WAN, Viptela. When they are forming the IPsec tunnel, BFD is there enabled by default. That means you don't have to do anything. BFD is automated or encoded there inside the data plane to detect the IPsec tunnels. Okay, we can go to the next switch and we can enable the BFD in the asynchronous mode. So now what does this mean by asynchronous mode? Asynchronous mode, that means that you have to go and enable the BFD in both the neighbors, so neighbor A and B, and then BFD will come into the picture. It has three characteristics. It has TX, it has RX, TX that desired minimum transmit interval, RX that is required minimum receive interval, okay, and then is failure. Detect the multiplier in terms of failure. So suppose you're sending the hello packet after every 20 millisecond and expecting that you will receive also after every 20 millisecond. And if you go and give the multiplier of 3, that means after 20 milliseconds, not in seconds, so 20 milliseconds. So after 60 millisecond, you will detect that the peer is not responding, and then you can take the action that peer is unreachable, etc. Correct. Now, good thing about BFT is this, that you can go and attach the BFT with different type of network protocol like OSPF, ISIS, EIGRP, any type of networking protocol we can go and attach with them, first thing. Second thing, even we can go and link BFT with IPv6 as well. We can link a BFT with HSRP, VRRP, etc. Okay, so wide range of protocol is there that is supported by BFT. Now let's understand in this diagram that how BFT is helping OSPF to form the, first of all, BFT neighbor relationship, and then we'll check the failure scenario. Correct. So here you can see that what is happening, that OSPF neighbor is forming, and we are going to do the configuration as well. I'm going to take example with respect to ISIS. So in our lab, ISIS is running. On top of ISIS, we'll go and configure the BFT. So you have your OSPF neighbor, they are up and running. And then once you go and configure the BFT inside OSPF, then BFD will start working in between the peers. Correct? Now, what will happen if there is failure? So in case of failure, because we know that BFT, they are working in sub-seconds. Okay, and OSPF hello timer is much more higher than BFT. That thing we know. So what will happen, that once you establish the BFT session in between two neighbors, and you can see here that as per your OSPF BFT configuration, you have established the BFT relationship or BFT session in between two neighbor. Correct? Now, what will happen, suppose if you have any type of failure, you can see the failure is there, some link issue, unreachability, high CPU, device reboot, etc. There may be so many different type of failures. So in that case, the BFT, they are sending, receiving TX, RX, and then the multiplier in between. So after 3 consecutive uh, multiplier, suppose if your multiplier is 3, so after 3 consecutive transmit, you are not getting any receive, and then you detect that, okay, after maybe 100 millisecond, you find that the peer is unreachable. Correct? And we know that 100 millisecond is 1/10 of second. So once the BFT will detect as a lower protocol, then it will go and inform the upper protocol. So BFT will go inform OSPF that your neighbor is unreachable. You have two options. Either you shut down the neighbor, that means you break the relationship with the neighbor, or you reconverge your protocol and try to find some other way to reach to the neighbor. Okay, and that's why the convergence will be faster with BFD. BFD is helping protocols to do the convergence. Uh, if you have alternate path as a routing protocol, then you can go and look for the alternative path. So what is happening here? You have two devices, you are running your higher protocol OSPF. We are going to check this inside ISI. So I'm running, for example, ISIS, and then I have my BFD profiling. So that means the BFD, so first of all, your ISIS is running, ISIS, and then your BFD, I'll put inside this, not here. So I have my BFD as well. BFD, they are using, for example, 1/10 of second to send the TX, and then RX is also 1/10 of second. Now, if any failure is here or here, because it's a bidirectional, so any place if you have the failure, then after 3 of 10th, 1/10 of second, 1/10 of second, and 3/10 of second, like that. So I'll make this that 1/3 of second. Anyhow, you come to know that okay, there is a failure, and then you will go and inform the upper layer protocol that a protocol, your agency, your neighbor is unreachable or having some issue. Can you check some alternate path if you have any backup path to reach to the neighbor, so you can reconverge your SPF algorithm and check alternatives. Okay, so like that, BFD is helping to reconverge faster. Now, how we can go and do the configuration? We have two modes of configuration. We can go and configure over global interface. We can go and configure over the interfaces as well. So we can go to the config, configure it, or we can go to the particular interface and configure it. If you want to disable it, you can go and use no feature BFD, so BFD feature will get disabled. We know that in the Nexus switch, we have to go first of all and enable the feature called BFD, and then you can do the rest of the configuration. Okay, so in terms of global parameter, how we can do the configuration, you can go to the global mode, say conf t, and then you can go and configure BFD interval. First of all, you have to give the TX. TX is not given here, but first option will be TX, and you can read the purpose here. So TX is 50 millisecond, and then minimum RX. Again, we are giving 50 millisecond, and then a multiplier is 3. Okay, and we have discussed about what does it mean by TX and RX. You can refer this particular slide as well. So minimum transmit interval, the interval at which the device want to send the BFD. Minimum receive interval, the minimum interval at which the device can accept BFD hellos, and then you have the multiplier. Great. So this is the configuration command here. You can see, let me highlight only the configuration here. So BFD interval 50, minimum 50, multiplier 3. And you can see what's the minimum, what's the maximum, and what's the default value here. Okay. Now over the interface also, we can go and configure like this, but we have some other options as well. So first of all, if we can go to the interface, we can do the configuration related to BFD like we have done in the global mode. And then if we want, we can give the key as well. So BFD authentication key, that's the first thing. And there are some other parameters as well we can go and give to the interface as well. So I will go and I'll show you that some other parameters as well we can go and provide. Okay, but so very minimum that you can go and enable the BFD. If you are in the Nexus switch, enable the feature, go to the global mode and run this command, or enable the feature, go to the particular interface and run this command. Great. So we are going to check the BFD configuration over ISIS. So I will go and run this BFD over ISIS, and what we'll do, we'll go and check over the interface. Okay, what you need to do, you have to go and check over the interface, because I want to do it over the interface. So we'll go to the interface, and then we'll run ISIS BFD. Okay, and then we'll go and even go and check the configuration related to BFD as well. So I'm going to show you this ISIS BFD in a while. Before that, let me go and complete this particular section. I have few examples related to other protocols as well to show. before going to the lab. So for ISIS, you can go to the router ISIS, you can enable BFD. You can go to the address family. If you have IPv6 address family, you can go to the address family, you can enable the BFD. So here you can see BFD example feature, BFD, if you have protocol feature OSPF, and over OSPF, you can go and enable like this. Over EIGRP, you can go and enable like this. Over IPv6, where you are using OSPF version 3, you can go and enable like this. Okay. So it is supporting, it has a wide range of support, and we can go and enable over almost all the routing protocols. All right, so let me log into the lab section and let's go and configure the BFD related to ISIS. Here you can see in the diagram that in between R4 and R5, what interfaces we have. So R4, I have gig 0/2. R5, I have gig 0/1. So I want to enable BFD in between that. So let me go to R4 and let me go to R5. And what we can do here, we can go to the interface and we can enable that BFD feature. So inside R4, the interface is gig E 0/2. So let's go to gig E 0/2, interface gig 0/2, and then we can go and give BFD. So let's check if we have ISIS BFD here. Yeah, we can go and enable ISIS BFD. And now we have the syslog message. So BFD session created, BFD session created with the neighbor. Okay, and what we'll do, we'll go to this side. And here also, we can go to the interface gig 0/1 and we'll give ISIS BFD and 45.4, 45.5. So with this peer, the BFD session has been created. Now what I can do here, we can go here and we are already over the interface. We can shut down the interface. At the moment I shut down the interface, you'll see that BFD session destroyed, BFD session destroyed, handle high, process ISIS, handle act, and administratively down, BFD is down. So at the moment the interface is down, you can see that BFD is down and it is telling that ISISC BFD is down. You can check your neighbor or you can reconfigure the protocol. So here also you can see we are getting the message. So this is the way, it's very easy to enable it. And because this is the iOS platform, so here you have simply one small command to enable it. If we'll go and enable it in the Nexus, so we have the option to do the configuration related to TX, RX, and the multiplier. All right, so we have checked the BFD. Let's stop here. Thanks everyone for enrolling this course. In this course, you will learn all the technologies related to CCIE Enterprise. But in case you are looking and you are preparing for your lab exam, please feel free to contact. We are running some sort of 100% guarantee program to make you pass. I will provide you the lab, resources, everything. If you want to know more about this offer, you can go and email to this particular address. Anyways, in this course, you are going to learn all the technologies. This will be very useful course to you. But in case you are planning to write your lab exam, just feel free to contact us. We'll provide you all the guidance, all lab related tips, techniques, all the passing techniques, etc. So please do not hesitate. Feel free to contact us and we will provide you and we will assure you that you pass your lab exam in first attempt. Thank you.